Howdy. So we're going to start the lecture for this. This is going to cover the remainder of chapter 4, and it's covering the material that we weren't able to cover in the last class, and the material that we would have covered in class on Wednesday if I was able to show up to class today. So again, do not show up to class this Wednesday. So that would be on September 27th. This will be in place of that. This chapter is the last chapter that's on exam 1. Exam 1 is on October 2nd, so next Monday, October 2nd. And I'll be covering chapters 1 through 4. I'll post another video that briefly go over the review sheet and also go over the chapter 4 lab in a separate video. So we'll be looking out for that. Chapter 4 talks about the relationship between two variables. So just in summary, we're looking at how one variable affects another. We talked previously about the correlation coefficient, and then we briefly started talking about how do we find a regression equation or a line, the best fit line, given more than 2 data points, like you would see in algebra. So scrolling down, I'm going to go to the slide that we ended off on last time. We previously ended off on this slide talking about residuals. Residuals is a key concept just to understand how we go about this. So we're briefly going to go into the whole process. And again, the main issue is, as you can see on this graph, for example, this graph right here, we have 6 data points total, 1, 2, 3, 4, 5, 6. There's no way to just do a line between 2 points that's going to represent all 6 the best. So we've got to somehow incorporate all 6 points into a line. Whereas in algebra, you would just draw a line between 2 points and that'd be your best fit line. So that's the fundamental issue. The concept that we get at is something called residual. Basically, it's how far is our point away from our line. So in this case, you can see 6 points, and residual just would be that distance from that point to the best fit line that we're looking at. So it's basically how close is our line to matching points that we actually saw in reality. This is an important concept just because we're basically essentially minimizing these residuals is what we do to find the best fit line or the line that best predicts what's happening here linearly. So first new slide is right here. I know some of the formatting's a little off on this, but basically what you're looking at is least squares regression line. It talks about minimizing the sum of squared residuals. So sum of squared errors, residuals, basically an error, residuals equivalent as far as what we're concerned for this topic. So the idea is for all of our points, we want to minimize how far those points are away from the line. So we want to find a line that has the closest for the most points. Is the basic idea here. It's called least squares because we actually do look at the square distance away, technically. We'll talk about the square part a little bit more, but just a little bit of background to what we're doing in statistics for this. Here's the equation. Again, we have a little awkward u there, but basically y equals b1x plus b0. Don't worry too much about these things for each side. Basically, just for our terminology concern, if you see a b1, that's referring to slope, and b0 is referring to y-intercept. So looking at algebra terms, b1 is the same thing as m, and b0 would be the same thing as b in algebra terms. So you can kind of see this as y equals mx plus b. It's the same idea. We just use a slightly different terminology. There's a reason behind it. I'll need to go into the full reason, but we basically have just slightly different terms. So b1 is the same thing as m. It's the slope. b0 is the y-intercept for this. But nothing too fancy. Just think about this as y equals mx plus b, just with slightly different terminology for it. So this is the same drilling data we've been using throughout. And what we want to do for this is we want to actually find the best fit line for this. Then we're going to look in particular at 130. We want to find a prediction at 130, and we want to see if that prediction is above or below the point that we actually found. So is our actual point, so this point right here, if you can see my mouse, point right here, is this above or below what our best fit line says it would be? And again, we're looking at the depth. So we're looking at how deep are we under the earth when we drill? How long in minutes does it take us to drill an additional 5 feet? So here is where I want to pull back to StackWrench. So then the previous slide, I'll show you or in the previous, or the following slide, I'll show you the menu for it, but you can see this also on this end. So let me pull up StackWrench for this. Now, I recommend for the homework that you use StackWrench on the test. If I ask you to do something related to this, I'm going to give you StackWrench output for it. So we want to look at the same thing. Go into our group, the same group page we've been using throughout the semester. And we're going to scroll down to this chapter 4 drilling depth data. Open this. And again, we have the exact same data set. So we have the depth and we have the time it takes to drill an additional 5 feet. I'm going to enlarge my screen just a little bit just to make it a little easier to see. And so the item you want to use is, again, stat regression simple linear, the same one we use for correlations, stat regression simple linear. And the exact same process again. So stat regression simple linear, we're going to use our depth as our x variable and the time as the y variable. And generally for this, you're not going to have to do any of this extra stuff. So just deal with that initially. Click compute. So we're looking for the least squares regression line. And this feature will automatically give that to you. So you'll notice right here is kind of the key thing we want to focus on for now. So we have the correlation down here. We got 12 total points. And here you actually have the equation. So we have the first value is the y-intercept. It's a little inverted, so don't get this too confused. It comes out a little different looking than it would on a, so that's not the slope, that's the y-intercept instead. So we have a y-intercept of 5.52, and then we've got a slope of 0.01155 for the depth. You can see that's multiplied by the depth, so the x variable, the y variable right here. Again, just to give you reference, this would be the best fit line for those 12 points. So again, I highly recommend that you use stat regression simple linear on the homework because that's going to make your life a lot easier. And again, on the test, I'm not going to require you to calculate this by hand. The equation is actually fairly complicated to calculate them. It's very tedious to do so. So again, I'm skipping that part. We'll focus on interpreting these equations and understanding these. So going back to the PowerPoint, if I can pull it up. So you're able to get this equation from StackWrench. So, and right here, so B was asking, let's find the prediction at 130. So at 130, let's find what we would predict the time it would take to drill additional 5 feet. So to do that, this would be something I would require you to do by hand. So B is something I could definitely ask you to do by hand. Simply plug in the value for X and you can solve for the value for Y. So in this case, we had we have a drilling depth of 130. We plug that in for X and we solve for Y is equal to 7.035. And C is just comparing those two. So it's talking about which one, how does it compare? So we actually observed a drilling time of 6.93 seconds, or minutes should be. This is a typo, it should be minutes in these 3 spots. So we observed a drilling time of 6.93. When in reality, and for our equation, we predicted a time of about 7.035 minutes. So this, what we observed is actually below what we would expect, is what we're seeing from this. Again, just as a reference point, same graph. I think the drilling time right here is 130. So notice it's below that best fit line. So again, the observed value was actually less than expected for this. So we go into the interpretation of these things, which is very key. So this is something I'll probably focus on a little more on the test. we'll discuss this a little more, but I want you to be able to interpret these quantities. So slope and y-intercept, they have pragmatic interpretations to them, so they're very useful to look into. So in the case of this equation, so we found a slope of 0.0116. What slope is always saying is for each additional change in x, how much does it change y? So in this case, for each additional foot in depth we drill, we have an additional time increase of 0.0116 minutes. If the slope was negative, that means for each additional depth of foot we go down into the earth, we get a decrease in time, so time would go down. It's positive though, so that means that as we get deeper, it's taking us longer to drill. So again, be careful, make sure you know what you're interpreting on the slope because it's very pragmatic how we can interpret this. I'll give you a second example in a second too on this. Y-intercept, so there's a lot on this slide, but basically we have a y-intercept of 5.5273 for this case. So y-intercept is simply what happens when x equals 0. So what's the value for y when x equals 0? The thing about y-intercept is it's not always interpretable. So you really have to answer these two questions in this case. So is 0 a reasonable value for the x variable, the explanatory variable? And likewise, do we have any values close to 0? We don't want to be using the y-intercept when it's far away from what we actually have observed. So in our case, 0 would just represent the drilling at the surface of the earth, since 0 would be 0 feet deep. And we do have an observation that's reasonably close to that. So it's only 35 feet away. So it's not that far outside of our model. So basically how we interpret this is at the surface of the earth, we expect about 5.527 minutes to drill 5 feet deep. So again, be careful with y-intercept. It has to be interpretable. It's not always interpretable. Big caution related to this. Actually, let me go back before I get to that caution. So let me do a second example here. So going back to StackWrench, we're going into the group page, and there's a second data set I want to look at. It's roller coaster data. This is a real data set. Again, just found under our group page. Way to get to that, if you've looked at our groups, My StackWrench groups, you should have it listed under there for yourself. So if you're just looking for the group that you have saved, you should find it there. Again, we're going to be using this throughout the semester, so just get used to it. And we're looking at roller coaster data right here. So these are all real roller coasters across the US and other countries also. See the first year from California. Different things are tracked for it. So we have the park that they're in. There's actually quite a few from Six Flags over Texas, the one in Arlington. So I actually recognize quite a few data sets in this, or quite a few roller coasters in this data set. Different type. Type is just the type of roller coaster. Is a steel versus is a wooden. You see those two pretty much the same column. Height's the maximum height. Likewise, speed is the maximum speed, miles per hour. Height's, I think, in meters. And we have various other things related to it. So again, real data that's tracked across roller coasters. Not every roller coaster in the world, but quite a few roller coasters in the world. I think we have about 400 total roller coasters for this. What I'm going to do is I want to briefly do a regression for this. So I'm going to do stat regression simple linear. Again, this is like your go-to feature for this entire chapter. The only feature in StackWrench you need for this entire chapter 4. Click on that. So my x variable in this case, I want to use the height of the roller coaster to predict the speed. So again, this is max height predicting max speed. If you think about that, it does make sense that these two things will be related. So the taller the roller coaster, you expect the faster the roller coaster. Again, this is real data though. There's a lot of things going into this, but that does make a lot of sense that those would be related and one would predict the other. If I click compute, what I want to focus on is a few things for this. So if you notice, the correlation is really high for this. If I go to the next screen, I'll go ahead and show you the relationship. The the graph for this. Then we'll circle back to the interpretation of the slope and the y-intercept. So for this is the graph for it. So again, I have the max height. So I have some really short roller coasters that don't really get up that high. I've got a few really, really tall roller coasters over here. By the way, general thing in Stackbench is that you can actually find the roller coasters that you're looking for over here. So let's say I want to find these two roller coasters that are really tall and tend to have a really high max speed too. You can actually find them behind the scenes there. So we have Superman the Escape, that's in Valencia, California, and Top Thrill Dragster in Cedar Point, Sandusky, Ohio. So these are the two tallest and also the two fastest roller coasters in this data set. I think they're actually the two fastest in the US also. I think I looked that up previously before too. Regardless, you're seeing a really strong trend. None of the points are very far from the line. There is some random scatter still happening there here, but this would be a strong linear trend. So I would expect you to be able to look at this and see that, yeah, it's got a positive correlation and it's a pretty strong correlation too. So it's not a mediocre correlation. It's, you know, it's pretty high. It's above 0.8 for sure. But going back to the topic at hand, we want you to be able to interpret these quantities, or I do for these quantities. So first one is for slope. What does the slope mean in this case? You're lucky I can't randomly spin people on a recorded video, but if I could, I'd definitely be asking that question right now to somebody. So what is the interpretation of this slope? Think to yourself just for a second. Always, slope is the change in x. How does it affect y? So how does the increase in height affect the speed? What this is telling us, for each additional meter you build a roller coaster taller, like for the max height, you're expecting about a 1.4 mile per hour increase in max speed. So for example, if I build a roller coaster 10 meters higher, then I'd expect about a 14 mile per hour increase in max speed. So again, that's pretty relevant if I'm a roller coaster builder. I need to kind of know that. Second question I would have asked somebody, again, I can't spin for anybody. I thought about playing the sound effect just to freak you guys out, but the y-intercept right here. So this 32.279 is the y-intercept. What does this mean? Is this interpretable for this data set? So in this case, the y-intercept is always what happens when y equals 0, or when x equals 0. So what would happen at a height of 0? So does it make sense to interpret a roller coaster with a 0 height? Be a follow-up question. In this case, I'd argue no. This really makes sense to have a roller coaster that doesn't have any height, and you wouldn't expect a roller coaster necessarily to have a height, just be completely flat. Technically, that sort of works, but I guess roller coasters tend to have some kind of height. If we look at our data set, all of them at least are somewhat tall. So you could sort of interpret this, not the best interpretation overall, though. I would tend to say this is probably not that useful. So anyways, that's just one other example of interpreting things. Just be careful interpreting the y-intercept, and the slope is always the same. It's how does y change when you change x? So one unit change in x, how does it affect y? The explanatory affect the response. The big caution sign right here, we do not want to do any kind of predictions in regression outside the scope of the model. So we're very conscientious in regression not to do something that is beyond what our model says we can do. I'm actually going to show a video that highlights this point. So again, the point is if I have a range from, let's say x is from, in the roller coaster case, I think it goes from a height of about 10 meters to a height of about 200 meters. I wouldn't want to use that data set to predict the height of a roller coaster that's 400 meters tall, because that's way outside the scope of my model. So I'm actually going to show you a video real quick. This is an example that relates to this, so just bear with me on this.
Minus 21 seconds, and the solid rocket booster engine gimbal now underway. T minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Good roll program confirmed. Challenger now heading downrange. Engines beginning throttling down now at 94%. Normal throttles most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%. 3 engines running normally. 3 good fuel cells. 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning, it looks as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side.
So I'll stop there. I just realized halfway through the video, I'm guessing you guys didn't get the recording of that or the sound on there. So you saw the video, but not the sound. You can look this up on YouTube, just the Challenger Space Shuttle disaster, if you want to see another video of this. So I didn't bring this up just to show a sensational video. Really, there's a reason behind it. And there's actually a core issue that happened with this disaster that is very similar to what we're describing right now. So let me go and show you some data on this. Okay, let me pull up my notes. Hopefully you can see this okay. So a little hard to see. So this is an old graph that they had. So Challenger explosion was back in 1989, or in 1986, I believe. That was the date for it. What you're seeing on this graph is the points of data they had for different times. So the Challenger explosion happened due to O-ring failure. So O-rings are essential for keeping the maintaining the stability of the aircraft as it's going up. And they're actually designed to where a few of them can fail and it's okay. It's within the realm of safety for a few of them to fail during the time period, because again, there's extreme stress going on a space shuttle when it's launching off. What you're seeing on the black points is temperatures, and then also the number of O-rings that failed at different temperatures. So each dot represents a space shuttle launch by the US. And so you're seeing at different points. So you're seeing in degrees Fahrenheit over here, not many failures happening between 65 and 80 degrees Fahrenheit. We had a few over here, but in general, most of them were relatively no failures for these O-rings. If you go back down, there's a few failures at the 55 to 60 degree range for Fahrenheit. We had one launch that's under 50 degrees, 55 degrees back in 1986. So the data, this is the data that NASA had at the time. So they had one launch, and that launch actually had closer to 10 or 11, it looks like about 11 failures back for the SRM-15. The big issue, so I mean, you couldn't hear the sound of the video, but they actually had a lot of delays on this launch. So it was launched January 27, 1986. The temperature was around 26 to 29 degrees Fahrenheit, so below freezing. The issue was that NASA kind of used this data that they had previously, and they just made a regression line between this. So they basically just made a best fit line. Not the one you're seeing in dots, but basically a line that kind of goes through here, if you can see my mouse okay. They predicted that, hey, we roughly have, 15 O-ring failures at this launch time. The problem is, that was based on faulty assumption, because they didn't have any data that was anywhere close to how cold it was the day they decided to launch. In reality, what you do see in this case is something more like this. It's more of an exponential trend. And they saw a lot more failures of the O-rings than they were expecting. So again, why am I bringing this up? Just a very powerful demonstration of a real example of why you should never use a regression equation outside of the scope. So outside of the scope would be if I have data in this case, if I, as NASA, I have data from 52 degrees to 82 degrees, I really should not only use that data within that scope. So I can say with relative confidence that how many O-ring failures I'm expecting within from 55 to 80 degrees. Maybe a little bit below, maybe a little bit above. But in this case, we're talking about 25 degrees below any previous data. There's no way for us to use this data over here to really accurately predict over here. So again, just be careful. Do not go outside of the scope of the model when you're doing regression. So let me show you a few more things on regression. So a little aside here, but you know, I really want you to understand these equations a little bit better and if their resistance, how these things are affected. So I'm doing applet regression by eye is the applet I'm using here. This is something you could play with on your own if you just want to get to know these regression lines a little bit better. So applet's regression by eye is what I'm using briefly here. Let me make the points a little bit bigger just to make sure they're seeable on your screen. So the idea of this is we can actually look at regression. So if I was doing this in class, I spend a little more time here. I'd try to get you guys to guess the best fit regression line. So I can move this around. I can try to guess at where the best fit line would be. What's really happening, so my guess would be in the green, and the red was the reality. What's happening is, a game I like to play with my classes, what the red line is actually minimizing SSE. SSE stands for sum of squares error. It basically stands for minimizing the square distance away from the point. So it's minimizing those residuals we talked about earlier. A tricky game I like to play with people is try to get a sum of squares error by moving this line around that's lower than what the red line has. It's a tricky game though because mathematically it's impossible. I can never do better. No matter how I move this thing, this SSE, these errors are going to be sum up to be higher than what the best fit line would be. It's called the best fit line for a reason. It's the optimal line for minimizing these square distances away. So a few things I want to show based on this. So this line's always going to try to find the best fit. It's done mathematically, and again, it's just minimizing those residual differences away. Let me go and show you a visual to try to capture that a little bit better. So I'm going to turn on these little boxes for squared residuals. It should help visualize what's happening with these things. I'll make the points a little bit smaller too. Okay, so what's happening here is each box represents a residual squared. So it's a square, it actually represents how much is that residual affecting the best fit line. So in this case, the game becomes like, can I minimize these boxes? If I minimize these boxes, then I'm minimizing the SSE, the sum of squares error. Again, I'm trying to least squares. That's essentially where the idea comes in, minimizing these square distances away. So no matter what I do, I'm simulating a couple more. They're going to be different for you if you play this with this on your end. I really want to minimize these boxes away from it. If I turn on the true regression line, you'll see the best case scenario. So if I have these points, they're as close to the line as they possibly can be. So I have a line that best compromises all these points and makes these squares as small as possible. So again, these boxes are just a square distance away. So one thing I really want to show you with this is something that leads into the last section is how much does one point affect this line? So if I grab one of these points in the middle here, if I start moving it away, notice what happens to that line. So before that line went right through here, and now this line is way over here. It's getting bended heavily towards that one point. So before it was over here, notice how it bends heavily towards this one point. So the question I would ask if you guys are here, randomly ask is least squares regression resistant? So is it heavily affected by one extreme point? Based on seeing this, the obvious answer should be no, it is not resistant. So again, if I show this one more, if I go the opposite direction, again, it's bending heavily towards that point. And what's nice about this, you can kind of see why. That box gets really big really quickly. As a result, it has a necessarily large effect on this whole line. It's a little trippy, but I can actually move this around, and that line is bending very strongly towards one point. I can do the same thing with even a few more points. So if I do 30, let's just find one that's a really good trend here. So this will work. If I just move one of these points over, again, the line's not going to move as much, but again, it is bending towards this one point because it's farther and farther away from that where it should be, or where everyone else is. So that one point still has a pretty significant effect. Less of an effect than it did previously, but still a significant effect. The only reason it has less effect is because there's more points to it to counterbalance that one big box. So regression is not resistant. It is heavily affected by a few extreme values. That's the point I want to bring across here. And likewise, unlike algebra, what we're doing in this case, I'll put it down to a few points just to make it a little simpler to see, is we're just minimizing these boxes in a sense. We're minimizing the differences. So I want to find a line that has the smallest boxes possible, the smallest errors away from this. Is visually what's happening. Again, you're not required to calculate this by hand, but this is kind of just showing the concept behind how we find the best fit line for this. And that was section 4.2. So we're going to wrap up on 4.3 and we'll be done with this chapter. So 4.3 just talks about diagnostics for the regression line. So just a couple of things we talked about. One's actually related to something we just previously showed. So relatively short section for this. The coefficient of determination is a big deal, and then we're just going to talk about influence points, which we were just previously talking about in a sense. So coefficient of determination. So a new concept, this is heavily related to the correlation coefficient. So a coefficient of determination, R squared, it's measuring the percent of the total variation in response that is explained by the least squares regression line. So basically what it's saying roughly is what's the percentage of y that can be explained by x? What's the percentage of the response variable that can be explained by its relationship to the x variable? Just to hit this home a little more, so it's from 0 to 1 inclusive. So 0 would be no relation, 1 would be they're 100% related. So x completely predicts y. So you see that here. If r squared equals 0, there's no explanatory value from this line. That means x does not explain y at all. If r squared equals 1, that means 100% of what's happening to y, the variation in y, is explained by x. What's nice about r squared is that r squared is simply r squared. What I mean by that is, if you remember, we used r for the correlation coefficient. So if you want to find r squared, you can just square the correlation coefficient to find r squared. So to determine r squared for the linear regression model, simply square the value for the linear correlation coefficient. So there's a little caution here. Just basically, if we're looking at nonlinear lines, this wouldn't work. But basically, for linear equations, if we're looking at the linear explanation of this, then this is the case. R squared is just the squared version of r. So if I give you r and I ask you to calculate r squared, well, you simply just square r. R would be the correlation coefficient. So if it's a correlation of 0.9, then r squared would be 0.81. It's just 0.9 to the power of 2. Here's a few data sets that I want to look at real briefly for this. basically you have 3 different data sets. I'm just going to show you how the R-squared varies for these. And again, these are very pragmatic. You need to be able to find the find how sorry, blanked out for a second here. Basically, how much variation in y is explained by x. So you see on the dataset A, this has an R-squared of 0.9999. That means that 99.9% of the R-squared is predicted, or sorry, 99.9% of the variation in the y variable is explained by the x variable. And you notice like the line perfectly predicts the y variable. I'm almost exactly dead on. Over here, you see 94.7% R-squared, so 0.94947 would be the R-squared. That means the vast majority of what's happening with the y variable is explained by the x. So about 5% of the variation is unexplained by this line. So you notice there's still some variation happening. Most of the variation is explained by this line. There's some that's not. And lastly, over here, you have a R-squared of 0.094. So the majority of the variation in the y is not captured by the line. Only about 10% of the variation is explained by the line in this case. So again, just interpreting this value. So in this case, looking at the drilling data, just want to show you the graph for this again. How would you find the R-squared for this? Well, this is the graph for it, as we previously saw. Same drilling data as before again, how deep we are, how long does it take us to drill additional 5 feet. So I'm going to go back to the notes on this, or the StackCrunch on this. I show this, so it's regression, simple linear, and I'm looking at depth to predict the time. Same thing we've done before. We end up with a R of 0.7728 right here, and an R-squared of 0.597. So what's the interpretation of the R-squared in this case? So again, the depth predicting the time. Rough interpretation would be roughly 60% of the variation in time it takes to drill is based on the depth. So roughly 60% of our time variation is based on our depth. So big picture, going back to the slides here on this, is you need to be able to find and interpret the correlation coefficient. So in this case, the linear correlation coefficient, if I gave that to you, is 0.773. That means that R-squared would be 0.773 squared. It's 0.5975. So that's the same thing I've shown in StackCrunch for this. Basically, that interprets to about 59.75%. So 59.75% of the variability in drilling time is explained by this least squares regression line. So the key from this is you need to be able to interpret R-squared, A, and also you need to be able to use R to find R-squared. So you need to be able to use a correlation to find R-squared or vice versa. So if vice versa, if I give you an R-squared, you'd have to take the square root of that to find the correlation. So if you just remember R is correlation, R-squared is, we call it R-squared. I'm not sure why we don't call correlation just R, but the coefficient of determination we typically just call R-squared. Just need to be able to interpret back and forth. The same exact relationship between the two as variance and standard deviation have. All right, almost done. Just talking about influential observations, and we'll be done with this chapter. Basically, an influential observation is any observation that significantly affects the least squares regression line. And so basically, it's a value that's far off what the line would be. And remember again, for regression, these lines are very much not resistant. When we mean resistant, we're talking about, are they affected strongly by extreme values? If the answer is they are affected strongly, then they're not resistant. They do not resist those values. So let's look at these this slide right here. So if you think about the influential points, always kind of visualize what's the best line for this. So if I'm looking at this, like these situations, ignore kind of the bottom part because in a sense, these are all really case 1 and case 3 are both influential. The reason why is if I had to draw a best fit line, it'd be kind of like this right up here. So if you can see my mouse okay, it's like it goes through there would be the best fit line. So notice how far off the case 3 and case 1 are both are from that line. Case 2 is right on the line, so it doesn't influence nearly as much, but case 1 and case 3 both are pretty far off that. So these both would have a big influence on this point. Because again, regression is not resistant. So these points have a big influence because if you think about it, they'd have a large residual away from that line. So it forced that line to bend towards them. So if case 1 was added, case 3 wasn't there, this line would have to bend this direction to accommodate case 1. The opposite of case 3 was happening. So let's look at this with our drilling data set. So let's suppose that we've had an additional drilling point. So all of our points previously were from a depth of 35 to 200. And now we're looking at a depth of drilling that's 300 meters deep or 300 feet deep. So the question would be, is this point influential? Does it have a big effect on it? So here's the graph of what it looks like. So again, all of our points previously that we looked at are over here. And then we add one point way up here in the corner. So would that have a big influence on this data set? The answer would be absolutely yes. Here's actually a visual of that. So in this case, I have all my points down here. This will be the regression equation if I ignore this one extremely deep point. If that point's added, though, you'll see the whole line bends quite a bit towards it. So one line does drastically change what's happening, or the one point that's deep in this case. So yeah, it's a very influential point. So basically, any point that's going to have a big residual, a big distance from the rest of the points, it's going to be influential with regression. So just some things to think about with this, and not necessarily testing over these, is really, if you're going to remove those points, we have to be very careful about how we do so. We don't want to cook our books. We don't want to just take out points to make our site look better. So if we do, we got to be very careful to note that to everybody that as a researcher, we took these out for this reason, and we make sure it's very clear what we did. And what's better to do in general is one of the two things below is either to collect more data, just to make sure those influential points aren't going to be as effective, especially if you find more data points close to those influential points, or at least around the same X values. And there's different techniques you can do also. We're not going to really discuss these in this class, but you can do some fancy mathematics to try to decrease the influence of those points so that they're not messing up your model as much. And that's it for chapter 4. So that's what we have left for this chapter. So again, this chapter will be covered on the test, and I'll post a separate video that talks about the lab and also the review for the test. And I'll stop the video there.